Hi guys, so finally we were able to train our own Llama 3 8 billion parameter model to generate 3D environments out of text prompts. So before getting into the Jupyter notebook, let's see the dataset that we have prepared to train this model. So I've prepared a dataset of 1000 input samples. So let's open one and see what the input looks like. So input is like create a 3D rack cluster, and it is in that we have defined how many rows, how many columns of the rack cluster we want, what's the distance in which it would be separated in terms of the x and y axis. Also we have defined the number of rows and columns within each rack, and within each rack there would be trays and the pallets, and on top of pallets we'll be placing up boxes. So we have defined all that, and also we have given all the assets that we have into the library with their dimensions so that it doesn't overlap with each other. So there would be like different objects placed within the 3D environment. We don't want any objects to overlap or go inside each other, so model will be able to understand all that information and create us a 3D environment. So that is like how our input looks like. And now talking about the output for the same input. So the output looks like in this way. So it is basically dictionary in which the key is the name of the asset. For example, if we see here, SM rack frame and rack tray were some of the objects that were required to build the 3D environment, and in this case rack frame is a list of transforms. So here transforms represent x, y and z axis of this asset. So for example, if there are, let's say, 100 items in this following list, so that would mean that 100 times this kind of frame needs to be placed within the 3D environment on these xyz coordinates. So I'll just go and maybe format this document to understand it in a better way. So now we can properly understand. So we have like different coordinates available for that rack frame asset which is there. Same goes for rack tray and the other 3D assets which are available. So that is the kind of output that we are expecting from the fine-tuned model, that given a text prompt, it should generate the transforms of each and every object that needs to be placed within the 3D environment. And here the transform represent x, y and z location of the asset which is represented by the key of the dictionary. So we can see like there are different boxes, and this is the kind of output that we are expecting for the Llama 3 8 billion parameter model to give us. So we were actually able to train such model, and it was also able to give us good output in terms of visual aspects. And let's go and see what we have done in the Jupyter notebook. First, we have imported all the required libraries. We have defined, so I've experimented with different versions to get a proper output. So that's version 6. We have linked our won't-be project so that we can see the training logs. After that, we have defined some parameters. So max sequence length is basically the parameter where we define what's the maximum length of the output which can be generated by the fine-tuned model. So that also we have tried with different numbers. So 32,768 is the one which we are going to use, and if there is the output which is more than this maximum sequence length, it is going to give us out some error. So that is the maximum length using which I was able to train and generate output on the GPU which I am using, which is A100, which comes with 80 gigs of VRAM. So this is the output directory where the model is going to be saved. And then using fast language model, we have first loaded up the pre-trained model. In this case, it is Llama 3 8 billion BNB 4-bit model, which comes with Unsloth. So Unsloth is a library which helps to train big language models if you have like limited VRAM. And then again we have like defined the model. So we are using PEFT model, which is parameter efficient fine tuning. So we have again defined that model with different parameters of LoRa and random state and so on. So once we do that, we can also see our GPU configuration, which is A100 80 gigs and maximum available memory which is available, and also the PyTorch and the CUDA version which is going to be used. Next comes our prompt template. So all the input and output which I have just shown you, we have to like modify it in form of a prompt template so that it is easily understandable by the Llama model to generate the output. So all the data set which we have of 1000 rows, we are going to pass it through the prompt template to make it behave in the way that we want. So that so in this process, so I just created one output CSV with all the 1000 rows and passed it through the prompt template, and now we have the data set of 1000 rows. Now comes the training part. So here we have defined different training arguments, and also if we see, we have defined how many epochs we require to get the model completely trained, and also we have the learning rate parameter and different other parameters, including the output directory where the actual model is going to be saved once the training is done. Okay, so after this we are going to print out our GPU stats. So in GPU stats, we can see again A100 80 gigs maximum memory, and also the memory which is reserved before training process. So that is that. And now using the trainer.train command, we have started the training process. So we can also see some of the information which is printed out, such as number of examples. So we have 1000 rows, number of epochs 5, batch size per device is 2, and different other options and configurations that we see, and total step size is 625, and number of trainable parameters also we see. So Llama 3 is a 8 billion parameter model, but since we are using a LoRa based parameter efficient fine tuning process. We don't have to train all the 8 billion parameters. We just have to train 41 million parameters based on the configurations that we have done. So now the training process has been started. So it took around like 10 hours, 25 minutes to train the whole data set. And we can also see the training logs here. So I'll just skip the training logs. So I left the GPU open for like overnight to complete the training process. And again, we are going to print out all the GPU stats and to see how much memory it took. So first comes the training time. So it took around 627 minutes, which is around, yeah, so it is around, I think, 10 hours. So yeah, it is around 10 hours of time which it took. And also the peak reserved memory, like what was the maximum memory used while training, it was around 57 gigs. And then we are just going to save the train model in the local directory so that it can be used up later. And also we have uploaded it to Hugging Face so that we can anytime download it and use it again. Again, we see the maximum sequence length and the output directory. So we have like 32K tokens which it can generate. So now let's start giving maybe some sample input to see what kind of output our trained model is able to generate. So here we have given a prompt, input prompt, in which we can see generate a cluster in which we have one row of the cluster, one column for the cluster, and also the distance between the rows and columns for the cluster again. And within each cluster, the rack should have only one row and only one column. And again, we have defined some offsets where the palette should be placed within the tray. And also we have given all the assets with different dimensions which are available within our 3D environment to be spawned. And then what we have done, we have again loaded up the model from the output directory, and we have given this input. So input is by the name of input text, and as you can see, we have first passed the input text to our prompt template so that it can behave in the way we want and directly pass it to the trained model. And then we have, as you can see, given a generate command in which we have passed the input tokens, and also now we are going to stream out the text, so it is able to like stream the generated text directly in the output. Again, we see like some of the configurations and all, like PyTorch version and the GPU available, and it has now started to generate a response. So this was the input and this was the response. So this response is kind of in a list way. So what we are going to do, we are just going to copy this response to actually know how this output looks like in a 3D world, and we are going to actually spawn a 3D environment using this response to know if it is actually working for us or not. So there is this Llama 3 output JSON which I've already created. I'll just save it and maybe format the document. Okay, I need to remove the extra content. So now it's formatted. We can see like we have different assets with the different transforms, which is the output which was generated by the Llama model which we have trained. And now we are going to use this output to actually generate a 3D world. So I'll just open the Unreal environment. So as you can see, currently it is like empty. There is no objects available here, but we are going to use our JSON to spawn different objects in the scene as we have given it in our input prompt. So there is this script which is going to read the JSON file, this Llama 3 output JSON file. We can also see the path, and then it is going to spawn different objects based on the transform which is available here. So let's go. I'll use the Unreal Python execute command, and we would be able to quickly see the objects which are spawned. So yeah, here we can see there are 2 racks which are spawned. So if I go back to our, if you remember the input that we have given, so I'll just open that. So this was the input prompt. I'll close this up to show up more. So it was one row and one column. So we can see there is like one row this way, and there is only one column for the rack cluster. So that is there, and then we have one row and one column in the rack itself. So if we like see a particular rack, so there is this one row and one column in this way. So if I'll go just closer to, so that we can clearly see it. So there we can see there is only one row and one column in one particular rack as we required. So it is able to actually generate the output which we required. Now maybe let's move to some other example, a bigger one, to actually understand how it is working. So this one, this particular example is a big one. So it has like 3 rows of rack cluster and 2 columns of the rack cluster, and every rack is going to have 3 columns and 3 rows and 1 column. So again, when I ran that, I was able to get some output in this form. So here we see like there's a big JSON this time, and the bigger the output, the more time it is going to take. So I think this one took around 10 minutes to generate since it was a bigger output. So I'll just copy this one and paste it in output JSON to create a 3D environment out of it. So I just formatted the document, and we can see how many rows. So there are 349 rows for the JSON with different transforms or different objects available. And then I again am going to use the script to generate a 3D environment. And we can also see like once we like run the script, it is going to clear the level. So it is going to remove all the objects within the environment first, and then going to spawn the new objects based on the output which the fine-tuned model has generated. Okay, so I'll just put it on one side and Ctrl+Shift+P, Unreal Python execute. So here we have seen like some differences, and now we can see it has removed all the previous objects and generated a new one. And now let's go to our input prompt to see if it has correctly generated the output as required. where is that? Okay. So let's see. So first of all, the cluster consisted of 3 rows. So let's see where are 3 rows. That is 1 row, 2 row, 3 rows. So there are 3 rows, 2 columns for the rack cluster. So 1 and 2. So that is exactly correct. And we have also specified the distance between rows and columns. After that, it was saying within each rack, there should be 3 rows and 1 column. So let's go to one rack and see if it is actually following the way we wanted it to. So there are 3 rows, 1, 2 and 3. So there are 3 rows and there is 1 column in the rack itself. So it is able to actually follow the instruction that we have given and able to spawn the 3D environment as required. So now we have actually, now we were able to actually spawn the 3D environment according to the text prompts that we required. But here we have faced one issue. So I'm going to now tell you about the issue that we have faced and that we want to tackle. So there is this input example 2, and in this we can see we want to spawn 4 rows and 5 columns of the rack and with some spacing, and within each rack we want 5 rows and 3 columns. So you can assume like this is going to be a very big environment that needs to be created, because there should be like 4 rows and 5 columns, and within that there are also going to be very big rack that is required to be spawned. So there is going to be like a lot of transforms of different objects that we are going to require. So when I actually ran that, I came across an error, which was the current text generation call will exceed the model's predefined maximum limit, which is 32,786. So it was able to generate the output. I can also just copy and maybe paste it here. As we can see, how many words are there? Okay, so there are no words. So as you can see, like there is this long output which it generated, but because of the maximum token length limit, it was not able to generate the full output. So that is the current problem with our model, and I would maybe require your help as well. So anyone, if they are seeing this video and maybe help us with identifying or help us to resolve this issue, that I would really appreciate it. That if there's a model and we have a predefined maximum token length, how we can make the model to generate the output within that, or if there's a way to increase that token length which can also fit in our current GPU, which is 880 gigs of memory, how we can basically use this model to generate the output, maybe in batches or some other way. There could be maybe some other way is like the way in which we have defined the output. So right now the output is in this form, where for every asset we have defined the transforms, the XYZ coordinates. If there is maybe some efficient way of defining these transforms for every object, for example, right now it is all the XYZ coordinates of all the assets that we want to spawn. Maybe there could be some other efficient way in which using lesser information we can define the whole environment which is required. So maybe that could be a solution, but I'm still like trying to figure out how to resolve this. So any help would be really appreciated. But yeah, we were able to actually get some output of the prompt that was given and generate a environment which really made sense in the 3D world. So I think the experiment that we were trying to do is now successful. Now it is more about how we can optimize the process of generating this environment, and also how we can figure out a way in which we can also generate large environment which could fit in our maximum token length that we have previously defined. So yeah, thanks for watching this video and stay tuned for more updates.